Welcome to our monthly online Zoom webinar series, Nodutalk, initiative by Castwell Foundries. In today's topic, we are going to cover types of magnesium treatment and potential recovery, specification of alloy, new type of nodulizer, selection criteria of ferrosilicon magnesium alloy or nodulisers, treatment ladle design, preferred residual magnesium, various summary of influencing factor on magnesium recovery, fading, and check and action in case of low nodularity. Now I hand over to Mr. Staff Hendricks.
Good evening, all of you. I hope we can have a fruitful meeting again. Types of treatment, the three types who are the most common is the sandwich, who is mostly used. We have the tundish cover, who is better and also very much used, and the wire injection. The most common nodulisers are ferrosilicon magnesium, and that's mainly for thick castings. Ferrosilicon magnesium rare earths is for thin and medium wall castings. Nickel magnesium is for high resist and eventually final small modifications when the treatment is done but the magnesium level is too low. Copper magnesium is used for high resist type 1, and the wire nodulising is medium size ladle. Please look very well. If you say ferrosilicon magnesium, in principle, then there is no rare earths. If you say ferrosilicon magnesium rare earths, then there is rare earths. This is the international, let's say, notification of it. And as you can see with Castwell, you can have a lot of types of these containing different percentage of magnesium, calcium, rare earths, aluminium, silicon, and so on. As you can see, the silicon and the aluminium is nearly all equal. So if you order something, ask information at Castwell, because the rare earths and the calcium can be different. Sizes are different from very large 15 to 25 for large amounts of metal, and very small from 0.5 to 3 millimeters for the small castings. And they are very well packed. The nickel magnesium is mostly starting at 14 to 16% magnesium. And you have the type with rare earths and the type without rare earths. As we say, they are not that much used unless high-resist materials, they are used very, very often. Sizes 10 to 100 or 25 to 80. The specifications, you can see magnesium 4 to 12, different types. Calcium 0.3 to 4.5, rare earths 0 to 7, lanthanum 0 to 2, silicon 43, 48, and aluminium 0.6 to 1.5. You can choose the one who is the best suited for you after you have calculated everything. The same for nickel magnesium and copper magnesium. Let's first talk about the use of lanthanum. Lanthanum is the last decade very much in the literature, and it seems to be a very, let's say, very, very good element. Let's have a look. Lanthanum is very reactive, and you can see it at the graph at the right side. It is very, very much for forming stable oxides as well as sulfides. You can see with the oxides, he is at the top, together with the cerium oxides, he is there. But also at the sulfides, you can see that lanthanum and cerium are very, very high. They are both much higher than magnesium. Have a look. Not as much for the oxides, but for the sulfides, they are very, very much higher. And the higher they are, the more reactive they are, and the more stable they will form oxides and sulfides. When you use cerium and lanthanum together, that has no benefit, because both are having the same function and both have the same activity. So let's say, or you take cerium or you take lanthanum. Pay anyhow attention, because in your returns, there will be cerium or lanthanum coming back, and that will possibly end up with an unpredicted final, let's say, percentage. Don't use them or don't mix them, please. Lanthanum has an advantage, as is mentioned by many suppliers and, let's say, also in literature. It has less risk for chunky graphite. It gives a higher nodule count. It has less risk for porosity, and it has better mechanical properties. If you can see at the right side, it's the graph we presented already a few times. Lanthanum and cerium have a similar effect and can both lead to the same degenerated nodules if we misuse them. I must say that up to now, I never have found already that lanthanum is used in very thick wall casting. What's up to me a thick wall casting? More than 100, 150 millimeters wall thick. There is very few experience about that, but for small walls, let's say 30 millimeters and less, it's used a lot and has shown very good result. The negative factor is, of course, it's costing more than cerium, but you have to use eventually cerium if you have these degenerated elements in your metal, like arsenicum, bismuth, antimonium, lead. These must be compensated, and that can only very well be done by cerium. So that can be a reason why you use cerium instead of lanthanum. The second negative effect is if you use it, make calibrations for these elements on your spectrometer. And I have seen during my many visits I did all over the world that people don't calibrate their spectrometer properly. So at the end, they don't know the exact percentage of lanthanum and cerium. Very important to take care of this element. How are we going to select the ferrosilicon magnesium or let's say ferrosilicon magnesium rare earths? It depends on the type of treatment. It depends on the charge material. As I said already, you can have a lot of degenerated elements in your charge material or not. It depends on the temperature of the treatment, the quantity of the treatment combined with the ladle size, the section thickness of the castings, the presence at the silicon at the time of nodulising, because silicon is mostly restricted, and the presence of sulfur at the time of nodulising. Let's take them now one per one. So the three elements that are very important and you have to select yourself is magnesium, rare earths, and calcium. As I said, the higher the magnesium content in the nodulizer, the more violent the reaction, and mostly the lower the efficiency. You can see that very well when you nodulize with wire. They have 70, 80, and even more percent of magnesium. It's a very violent reaction you will have over there. Second thing to remember is rare earths and calcium have the same effect as magnesium concerning the formation of oxides and sulfides. So that means if you add something with more rare earths or calcium, the magnesium can be less. Last thing is calcium has an advantage that it evaporates less compared to magnesium. If magnesium is reacted with magnesium oxide, it disappears immediately, but calcium not. And consequently, it will keep reacting in the liquid metal. It also decreases the violence of the magnesium reaction. So pay attention, the amount of calcium in the ferrosilicon magnesium you buy is important. Rare earths can cause chunky graphite if few or no nodule degenerated elements are present. It's cerium who can compensate the effect of antimonium, arsenicum, bismuth, lead, titanium. Keep an eye on that. And we have seen in the first seminar we did last month that you can calculate how much cerium is required. The added rare earths can be adapted to the required value by mixing nodulizer with 0 and nodulizer with more. Because if you calculate and it comes out that you need 0.8% of rare earths at the end, you can mix the one with 0 and the one with 1.5. in order to have the reaction you want. You can see that 1 kilogram without rare earths and 1 kilogram with 1.5 rare earths leads to an average of 0.75 rare earths. Please do that. So if you use ferrosilicon magnesium with rare earths, you should have also the one without, so that you can, according to your calculation, you can get the correct amount. The sandwich method. Everyone knows it. It's, let's say, I think it's nearly the oldest one type of treatment who is still using. Keep an eye on it. The height compared to the diameter is very, very important to have a very long and intensive contact between the magnesium and the sulfur and oxygen who is in the metal. Preferred is 2. 1.5 is the minimum. The second thing is, the better that the cover fits on the ladle, the higher the efficiency. And that's, let's say, that's very, very important, because you have a cover, and if it's deformed, you will lose a lot of your, let's say, magnesium oxides immediately. Then this is preferred to have a proper pocket, but is less critical than the sandwich treatment. Most common for this is ferrosilicon magnesium 6 and the ferrosilicon magnesium 6 rare earths 1.5. But you can also use 8% of magnesium, depending on the amount you need and the amount you can maximum add on it. The wire treatment is, let's say, the last one, and it's very good, but it has some, let's say, important things to be aware. The number of wires needs to be balanced to the diameter of the ladle. You can imagine that if you have a ladle with a diameter, inside diameter of 1 meter, and you put one wire inside in the center of it, that it's very difficult to really treat all the metal who is in that ladle. The second thing is that it's difficult for switching the chemistry of the nodulizer, because you need another wire then. So if you have a wire without, let's say, rare earths, and a wire with rare earths, which one you need? How are you going to do that? Some people have solved this problem by taking 2 wires at the same time, and then part of this is solved. What's not mentioned here is, due to the high magnesium content, you will have a lot of slack, and you have a somewhat lower efficiency. If the charge of the material differs, it's impossible to use a fixed addition and type. When I come in a foundry, I always ask, just for a test, how much ferrosilicon magnesium do you use? And then they say 1.3%. The wrong answer, my guys. It's the wrong answer. It can never be 1.3%, because depending on the returns, depending on the sulfur, depending on the degenerating elements that are in, you need to calculate another amount. As I said, arsenicum, bismuth, antimonium, lead, titanium, you will have to have another amount of rare earths for compensating that. You can mix again that you have the correct rare earths. The degenerated elements, where do they come from? As we said last time, they come from potentially, let's say, pig iron. Some pig iron have quite of them, and potentially from the returns. If you don't keep a good track of your returns and you mix them, then some returns are there with a lot, some returns are there with less. Also, the cerium content in your returns will always be different. Pay attention for that. It's correct to do, otherwise you have problems. The higher the temperature, the lower the efficiency. And there, it's because the violence of the magnesium reaction is much higher, and the gaseous magnesium oxides will evaporate quicker due to the lower viscosity of the hot metal. The formula is still there, and there you see the last part of the formula, that the temperature above 1450 is really very negative, because you will need more ferrosilicon magnesium to be sure that the reaction is okay. Then the amount of metal and the ladle size. Small treatment size will decrease the contact of magnesium with the iron, especially when the ladle size is also not correct. And you know, we we need a very intensive contact between the magnesium and the sulfur and the oxygen who is in the metal. So make sure that the lower your size of the treatment ladle is, please take a lower magnesium content, because a higher magnesium content will react more violent, and the contact will be less than when you take a lower one. And anyhow, the ladle should be filled and must be more than 1.5 concerning height to diameter. Small and high ladles, because you can do it, you can have a small ladle and a very high one to meet that requirement of 1.5, but pay attention, because your people in the foundry will complain that it's very difficult to pour with a high small ladle a cast. So the section thickness, it's mainly that the thicker casting is, the more, let's say, important the rare earths and the nodule degenerating elements are. So therefore, if you must give a general advice, then you can say for thin castings, less than 30 millimeters, take the magnesium 6 and rare earths 1.5. For medium, 30 to 100 millimeters, take the magnesium 6 and rare earths a half. That can be obtained by mixing 1.5 and 0, of course. It's up to you. And for very thick castings, more than 100, no rare earths, please, because rare earths will always go then to chunky graphite. So another thing was important is, at the time you are going to do the nodulizing, how much is your silicon then? Because every ferrosilicon magnesium has a lot of silicon that comes in, and later you have to do the inoculation. So then the silicon will go up very, very high. This is, of course, not true for a wire type nodulizing, because they have no silicon. Why is that important? First, if the silicon content is much too high, you will have difficulties to get pearlitic iron. And secondly is, when the silicon content is high, you get Sharpie V results at low temperature who definitely are not okay. The graph at the right side shows you the difference. If you go from 1.8 silicon, let's say, to 2.1, you immediately have already at 12 Joule for the Sharpie V, you have already from minus 30 to less than minus 20. And if you go higher from it's really 2.95, who is a little bit extreme, but you meet it sometimes, you will see that you can nearly never get the required results at low temperature, who are mostly a value of 12 Sharpie V. So silicon is to consider. Another point is, of course, that you can use nickel magnesium, but nickel magnesium will have, due to the nickel, a pearlitic type tendency, and can not that much be used for ferritic ductile iron. When the lower the magnesium content in nodulizer, the more nodulizer is added, and the more silicon will be added. If you add 1% of ferrosilicon 6, you add about 0.70% silicon. But if you use the magnesium 4, you need 1.5% to have the same amount of magnesium in your metal. But then there will be 1.05% silicon coming on top. That's already sometimes much too much for having a correct final chemistry of your iron. So the sulfur, the higher the initial sulfur content, the more nodulizer must be added. And this will lead to a lot of slag after treatment, who is difficult to remove, because the slag has to float up and will come quite some time after the treatment is already finished. And how can you let's say, decrease that amount of nodulizer a little bit is, if you use a nodulizer with a higher calcium content, you can decrease the amount of ferrosilicon magnesium you have to add. How much must the silicon content be in the metal? It's very difficult to say. I have seen initial contents of 0.020 and still giving the good result of the treatment. Some people go even to 0.010 and do a nodulizing treatment. It's more experience and it's more how your treatment is done. But please keep it as low as possible because it only gives some difficulty. Here you can see a little bit of difference between 15 to 25 millimeters and the 0.5 to 3. Pay attention that the smaller the size of the nodulizer is, the quicker you can lose some and the quicker it can, let's say, be attached to the side of the ladle, to the lining of the ladle, and so on and so on. So find out which one is shooting the best, and it's also related to the amount of cast. And you can see what Castwell is proposing, and I agree with that. If it's above 1 metric ton, so 15 to 35 will shoot very well. You can see a half to 1 metric ton. And if it's smaller than 250 kilogram, then you really have to look at 0.5 to 6 or 0.5 to 3 for having a good recovery, because everything must be dissolved in the metal and in a proper way, not too quick, not too late. Here again, we see some proposals for Noduliser. What is the preferred residual magnesium, rare earths, and sulfur in the casting? Because it's what's in the casting that is what's important for us. It depends on the time between nodulizing and pouring. That time we will have a fading, and we come back on that later. It depends on the presence of nodule degenerating elements, because they need the cerium from the rare earths for compensating these elements. It depends on the wall thickness of the casting. Why? When we stop pouring, the metal is still liquid, and the thicker the wall, the longer it stays liquid, and the more fading we can have. So it also depends on the wall thickness. And the residual magnesium content depends on the MgS relation. We come later on that because we will have a magnesium active and a magnesium on the spectrometer, but we come back on that. And it also depends on the relation between magnesium and rare earths. This is the graph we have seen already in previous month, but plus it's a graph who is very, very, very important. The green zone is the one, the relation between the magnesium and the sulfur. And the green zone has the best results. Left of the green zones, you have low nodularity, and right of the green zone, everyone says, okay, I have sufficient high magnesium. You will have carbides, you can get low nodule count, you can get shrinkage, you can get a lot of other things. Try to be in the green zone. If the sulfur is too low, you can have degenerated nodules and you can have carbides. If you see here, this is the result from 0.004% of silicon. You have several, the red arrows show you not good nodules, and the yellow arrows show you carbides. So don't think that the low silicon of sulfur content is the best. Definitely not. And the magnesium to the rare earths, this is also a graph who is very important. It's relative. You can see there is only mentioned heavy section and there is mentioned thin section. Please pay attention that the more rare earths you use, the lower the amount of residual magnesium should be. Otherwise, you are blank zone, white zone over there, and there you can get all different problems you never want. Try to be in the upper zone there for heavy sections, preferred, and thin sections. So, magnesium active, what is that? Your spectrometer gives you the percentage magnesium who is still in your metal. But that's also the magnesium who is bound with sulfur, MgS. And MgS has 0.75 times the sulfur content as magnesium. So magnesium active, that's a very important thing, and I always check it in every foundry I come. Whatever the sulfur is, you don't have to look at the sulfur, you can see if the magnesium active is still okay. And for different thicknesses, we can see let's say this very small one, 0.030 to 0.035. The magnesium active should be 0.25 to 0.030. Rare earths also can be fairly high. These figures come out of the graph magnesium, rare earths, magnesium, sulfur. It's a very good table you should put on the platform from your melting area so that the people can really look as well as the magnesium active as the rare earths. And magnesium active, they have to calculate. So how much do we have to add? That's what we saw last seminar already. It depends mainly on the residual magnesium you want to have. It depends on the final sulfur content you allow. And please, it must be minimum 0.006. Otherwise, you get problems with your inoculation. It depends on the percentage magnesium in your nodulizer. It depends on the efficiency, and it depends on the temperature. So again, this is next slide, because this is explained what I just said. Now, fluctuations. Everyone knows if you come in the foundry, you always say, oh, and we did this, and at the end, the result was different. Yeah, in principle, my friends, everything in metal melting and reactions is according to the law of nature. And the law of nature is very strict for everyone. It does not cheat us. So if you got a different result, you did something else than that you thought you have done. You can see the variations. Where can they come from? If your ladle has 50 kilogram more, to give an example, your final magnesium will be 6% lower, 0.06 lower. So it depends on that, but it's also for weighting the magnesium. It's everything you do. If you add too much ferrosilicon magnesium, you get more residual magnesium, and this is a change in percentage. Please check this very carefully later when you have the text of this, because everything you do there has an influence. The first pour or the second pour, the percent of sulfur variation. If your sulfur is not 0.01, but it's 0.015, you will have to add more magnesium, or otherwise you will get a lower final magnesium content. It's the same if you add magnesium and you say 6, magnesium ferrosilicon magnesium 6, but it's only 5.8, you will get a different result. This is a point why every supplier should give you the chemical composition of the nodulizer he is delivering to you, so that you can calculate with the real figure and not with the figure who is nominal, because the ferrosilicon magnesium 6 can anyhow have 5.8 or 6.2. First pour or another. If you take, let's say, you pour after 5 minutes or you pour after 7 minutes, it will have a different result, because there will be a fading, and the fading depends on several other things. But please, you see, you wait longer, you will have a different result. And the time to the last box of a ladle, it's the same. If you do it in 15 minutes instead of 10 minutes, you will have a much different result, or you have to add more ferrosilicon magnesium to get the same result. Every factor in your process is influencing. Please use process control for controlling that. Temperature, the same. Higher temperature, you have a lower efficiency, and your final magnesium content will be lower. And as a summary, you can see whatever you have, at the end it will lead to incorrect results, and it will cost more if you don't pay attention. And cost, we don't want to have a higher cost. The fading between the treatment and the transport to the mold, and for very big castings you still have some fading inside the mold, but not that much. And you can see the longer you wait, this is just an example. You can have the first, let's say 5 minutes, perfect ductile iron, and after 15 minutes you have nodularity lower than 10%. This is extreme, but it gives you an idea. What are the reactions that we have during the magnesium treatment? First, it reacts magnesium with oxygen. That's the oxygen from the metal, but also oxygen from the air who is coming in contact with it. It's magnesium plus sulfur. That's reaction from the sulfur from the metal, but later on also from the sulfur in the slag. It can react extra more. You have also magnesium can react with the lining. The lining, when it's acid lining, is SiO2, and you can see that when it reacts with the lining, your silicon will go up and you will have more MgO, the white powder smoke, who is coming out. And you can have the reaction with the slag and the lining, then you have, of course, both. You can have the magnesium sulfur, who is good that you have made it, but with the lining, it makes again silicon, it makes then magnesium oxide who is disappearing, and the sulfur is going back in your metal. So these reactions are happening in your ladle during the nodulising, and you will have to take it in account. So the fading, that's during the time that residual magnesium content will be lowered. After treatment, the higher magnesium content you have, the higher the fading will be. Therefore, fading of magnesium, that's a loss of magnesium, that's a higher cost, and keep the magnesium as low as possible, but safe. The temperature of the metal, higher temperature, higher speed of fading. The third is the slag. Some people say, okay, leave the slag on the ladle, and when we are at the mold, we will remove the slag. Please don't do that, because the magnesium sulfur from the slag will react with the lining from your ladle or whatever, and the sulfur will go back in the metal. And of course, the nature of the lining, silicon of acid lining, will have these reactions. A neutral lining will be much less sensible for that and will be better, but is costing quite some more. The summary of the important items, as we said, the initial sulfur content, the oxygen content in the iron before nodulising. There is always oxygen in our iron. The tapping temperature for nodulising, the ladle design and the pocket, the presence of the slag in the furnace and the ladle. Many times you see people who are using a ladle 2-3 times after another without cleaning the ladle. Please don't do it, because there will be an interaction. The covering of the nodulizer and the inoculant, the filling time of the treatment ladle, the chemistry and the size of the nodulizer, and the fading. These 9 elements are the important elements for our nodulizing. The initial sulfur content, we can see that we can calculate how much magnesium do I need for removing the initial sulfur content to the final figure I want to target in my casting. Final figure should always be equal or higher than 0.006% sulfur. More initial sulfur requires more magnesium, or a ferrosilicon magnesium with a higher calcium content, because the calcium is more reactive than the magnesium. You can see it in the graph at the right side. Calcium oxide is the most reactive one, and also that for the sulfur, you can see that the calcium sulfur is as reactive as the cerium and the lanthanum, but much more reactive with the sulfur. So if you have a high S content at the beginning, please use a ferrosilicon magnesium with somewhat higher calcium content. Oxygen, we have seen it last time. So depending on the TG that we can use, if we are below, the metal is silicon plus oxygen is silicon oxides. These are nuclei, but the content of oxygen is increasing. If we go above the TC temperature, the oxygen is removed, but also some of the carbon is removed. It's very, very important to find the balance between them, because If we are too long below Tg and not going over it, we will have a very high amount of oxygen, and our efficiency of the magnesium treatment will be low. If we go too long above the TC temperature, then we will have no nuclei anymore, and we will have that problem that the nodule count will be very, very low. The best method is stay as long as possible below the TC temperature, and just at the end, go about 10 minutes above it for removing the excess of oxygen. Tapping temperature, we don't have to come very much on that. The higher the temperature, the more magnesium loss there will be, and the higher the reactivity. So please tap low temperature. Ladle design, we come back on that, preferred more than the height to the diameter should be more than 2.0. The lining of the ladle, I should not use CO2 sands, because there you have also your oxygen and so on who can react, and please don't do it. And the pocket who is in your ladle should be able to hold all the nodulizer and inoculant and cover it inside the pocket, so that this material is not as a bump above the pocket. No, make sure that the pocket is as big that everything is covered very well. Here you see some examples from the pocket and the ladle. The ladle is a little bit restricted, but mainly for the pocket. All can be good. All can be good, but please find out which one is the easiest for you and the best to go. Number two, for instance, is very difficult to clean that pocket because it's too small. Number three will need a much thicker lining in the bottom of the ladle because you have the pocket in the bottom. Number four, that is that you will immediately during the tapping have metal on the pocket. That's also not preferred. Number five seems to me one of the best. The presence of the slag in the furnace and the ladle. Please clean the metal surface in the furnace before tapping, that you don't tap slag in the ladle. Clean the ladle properly before adding the nodulizer. I see many times then they are using the nodulizer already, putting it in the pocket, and at the same time they are cleaning the side of the ladle lining. Please do it separately. Otherwise we can have these two reactions or below it. Covering of the nodulizer inoculant, the pocket must be as big that the nodulizer and inoculant are completely below the top of it, and it should be rammed and covered by thin steel scrap. Pay attention that due to the fact that we add also some thin steel scrap, the final carbon content of your metal will be somewhat lower because in steel there is nearly no carbon. And the better covered, the later the nodulizer reaction starts and the better the magnesium recovery will be. So make sure that someone does it properly and someone else check it that it's done properly. The filling time. The filling time should be that quick that when the reaction of the magnesium starts, the ladle should be already filled 60 to 70% of the ladle. That's very, very important because then the magnesium will be in very well contact with the liquid metal. The second thing is never have a large distance between the furnace spout and the treatment ladle, because at that time there is a long and extensive contact between the metal you pour in and the air, and so more air will come in. So quick filling, having the ladle very close to the spout of the furnace. The chemistry, we have seen it. Magnesium addition must be calculated, and the higher the magnesium content of the nodulizer, the more violent the reaction and the lesser the efficiency. Nodulizer with calcium can reduce the required magnesium addition, especially when the initial sulfur content is high. And the required rare earth addition must be calculated knowing the amount of degenerating element. Too much cerium addition can lead to chunky graphite, especially in medium, but surely in large wall thickness casting. And you will have it. Don't think, not with me. Yes, if your cerium content is too high, you will have chunky graphite in the last solidifying metal. The size of the nodulizer also will influence the start and the time of reaction. So don't take two small nodulizers in a very big ladle, because then the reaction will start too early and your efficiency goes down. Try to have the best density in the pocket by the sieving of, let's say, the nodulizer. And a nodulizer, a good nodulizer, should have 3 to 4 important sieves concerning grain size. That's similar to the sand for the molds, then you have the best density. Fading, restrict the time between treatment and pouring. Clean the slack from the ladle. Cover the ladling during transport, because during the transport there is also a contact between liquid metal and the air. And when you pour, keep the lip as low as possible above the mold or the pouring box. These all elements are, let's say, influencing the amount of fading. If there are questions, please let them hear.
Mr. Mahesh Chavan has asked why liquid slag generated after magnesium treatment. What is the reason for liquid slag generation after the magnesium treatment?
Liquid slag is nearly always has to do with calcium, because calcium gives a liquid slag. Magnesium, normally not. Rare earths, normally not. So please look then at the amount of calcium you have added with your nodulizer. That's the reason for liquid slag.
Okay, so basically it's more the question, more the calcium, more is the liquid slag generation.
Yeah, but you can also remove the liquid slag by a good slag coagulant, as we say. But ask your supplier from the coagulant then which one you need to use when you have a calcium. And in that way, you can make the slag solid so that it can be removed easily. Always, calcium is the best element in iron and steel production, but calcium has the most negative effect as liquid slag.
One more question is from Mr. Chandrasekharan. What is the maximum and minimum pouring temperature, and similarly the tapping temperature for SG iron?
That's very difficult to say, especially tapping temperature, because the tapping temperature, in one of my books, I have calculated the tapping temperature starting from the liquidus temperature of an iron. And you will see that's different in every foundry. So giving one answer for that, it's impossible. The second was the pouring temperature.
Yes.
Well, the pouring temperature there, you have, of course, two different. First is your metal should be liquid at the end of the pouring. And I should say not only liquid, but liquid plus around 30 degrees C above the liquidus temperature. So that the metal, when you stop pouring, is all over liquid still in the casting, not yet solidified somewhere. That's the one thing. The second thing is that 30 degrees, and in small castings it may be even 50 degrees, is very important, because during the pouring you will have some inclusions. You will make some sand, you will have some sand inclusions, you can have dross. And that's something, let's say later this year, we will talk about the problems of inclusions in ductile iron, and dross is the most important one there. Every casting during pouring makes dross. If the temperature is too low, the dross will stay all over your casting because it cannot float up. When the temperature at the end of the pouring is still liquidus temperature plus 30 to 50 degrees C, the dross will float up and you will find it at the top of your castings, where with some extra machining stock you can remove it. But it's really, let's say, it's the most complicated question you can ask me. What is the temperature I should need? Because I must know how you do it. I must know whatever, and so on. Give you a very simple example. When you are pouring and you tap 3 ladles from the same furnace, what is your temperature? Every one of your people will say exactly as you said, sir. We keep the temperature on that. Forget about it. Secondly, when you have tapped and the removing of the slacks takes 1 minute longer, then you have already 1 minute longer, let's say, fading, but not only longer, the temperature also goes down. When the third thing is, and that's one thing, please go in your foundry and have a look at it. Never pour with the ladle 50 centimeters above the mold. It should be 10 for a small mold to maximum 30 centimeters for a very big mold, because there you make turbulence, you make contact with the air again, and contact with the air in ductile iron makes dross. And the higher you go, the more the risk is that you have dross. And I have to tell you something very important. Maybe some suppliers will not like to hear it. A filter will not filter dross. A filter will not filter liquid slag. So please prevent them and don't try to hold them with a filter, because it will not be possible. I did one of the books I have is how you can calculate in your foundry what will be the tapping temperature you need if you know the pouring temperature.
Yes, of course, it depends on foundry to foundry. We cannot generalize what is the ideal temperature for SGRN. The next question is again by Mr. Mahesh Chavan. He's asking, high calcium, it leads to a basin chalk up. Yes, it will generate more slag and will lead to the chalk up of the tundish, I think he meant to say. And his next question is how to eliminate dross in a high wall thickness above 100 casting.
First about the calcium, I should say use a fixed amount of calcium, let's say in your nodulizer. Then you will find out what the reaction is and how much you have to treat the slag to get it out. But if all at once you use a much higher calcium, you will have much more slag. And then all the technique and the procedure your people used for removing the slag with lower calcium will not be a good result for the higher calcium. So try to stay with the same amount of calcium all the time. And in very, very special things, you can use a higher. When the initial sulfur content is much too high, you use a higher amount. But pay attention then that the slag removing is much, much important and will be more difficult. That's the first. The second thing was, in a thick casting, how can we prevent dross? You know, dross is, I should say, dross, first, what is it? Dross is magnesium, silicon, and oxygen. And there is MgSeO3, and you have Mg2SeO4. This is made when the magnesium is high. Not the magnesium, the active magnesium is high. With a very high active magnesium, you will always have dross. Please don't ask me how to avoid it. If you don't decrease your active magnesium content, you will have dross, because the magnesium is so reactive that it will react with the silicon, it will react with the oxygen, everything it finds. First thing. The second thing is the silicon is fairly, let's say, restricted. You have a silicon range to get your final perlitic or ferritic ductile iron. The only one is the 4% silicon molybdenum. The 4% silicon molybdenum has a very high silicon content, and there they have a lot of problems with dross. So it's very important that you restrict the magnesium content in this type of metal very, very much. Otherwise, you always will have dross. The third thing is the oxygen. You know where the oxygen is coming from. The oxygen is coming not from the metal, as you are there at the place of the location of the mold, because the magnesium has removed it continuously. Magnesium, rare earths, calcium has removed it continuously. But then you pour. If you pour on 500 millimeters above the mold, you will absorb already a lot of oxygen again. So low height between the ladle and the mold. But the second thing is, and that's something I have always been fighting on, your first metal that enters the mold. What is your first metal? The first metal is the metal that enters the mold before the whole pouring system is filled. What is it? If you have your sprue, the metal falls down, and during it falls down, its section decreases until the bottom. During the decreasing of the section, it absorbs continuously oxygen, continuously. When the first metal falls on the bottom of your pouring system, it splashes. It encapsulates again the oxygen. And then it runs through the runner to the ingate. All the time it's in contact with air, extra air. And it's only when the whole pouring system is filled, then there is no air anymore. There is no turbulence anymore, and then you will have less. So please pay attention that if you have a pressurized system, it's very good because pouring system, because it's filling very quickly, but it's negative because the speed of the metal is very high when it enters your mold. So when you have a non-pressurized system, that speed of metal, the metal speed when entering the mold is lower. That's okay, but you have one thing, and that is that your sprue is not filling. And therefore, the best combination is pressurized, non-pressurized pouring system. Then you have the lowest contact with oxygen. In the casting itself, when the metal speed is good, that means I say it should be less than 0.75 meters per second, and if possibly half meter per second. If that's okay, inside the mold you will not form extra dross anymore. And the dross of the first metal, who is still there, should be floating up to the top of the casting so that it disappears in a slag holder or in the risers. Or you must make sure that your first metal is not entering your casting. You should bring it somewhere where it cannot enter your casting. And then many times I hear from, let's say, foundry owners, yes, sir, but if you design our pouring system, then it's costing much more. And then my question is, what's costing much more? A more expensive pouring system or a scrap of casting? That's the decision you have to make then. And a good pouring system for ductile iron is not, let's say, very simple. It's not very simple. It must be pressurized, non-pressurized. It must hold the first metal, and then the magnesium active must be low, and then you will have very few to no problems of dross.
Thank you, sir. We will take a next question, Mr. Somin Roy. What is the ratio of cerium and antimony for the castings with thickness of 300 mm to 500 mm?
The relation between that in the previous session of last month, the previous session of last month, I gave ratio of cerium, let's say, to antimonium to and so on in a formula. And secondly, there are also the rules about the thickness, because you have two things. If the ratio is not okay, you can have a problem. And the longer a casting stays liquid, the more the time that your degenerating elements can make something wrong, or the more the time that your cerium, who cannot compensate degenerating elements, has the time also to destroy the nodules.